Over 400. That's the number of nuclear reactors operating worldwide right now, at this exact moment. It's a massive number, right? And it really sets the stage for the incredible global stakes we're looking at today. These aren't just some obscure backroom science experiments. They are literally the engines driving a huge chunk of our modern world.
So, welcome to The Explainer. Today we're demystifying the anatomy and evolution of nuclear reactors. My goal here is pretty simple. We're going to map out exactly how these absolute marvels of engineering work, taking you all the way from the basic fundamental mechanics right up to the bleeding edge of future technology.
Here's our roadmap for today. First up, how reactors make electricity. Second, we'll look at thermal versus fast reactors. Third, we dive into moderators, coolants, and cores. And finally, we'll wrap up with the 4 reactor generations.
All right, let's jump straight into part 1, how reactors actually make electricity.
You know, when you strip away all the sci-fi intimidation factor, the main job of a nuclear reactor is actually remarkably straightforward. It's designed to extract the intense heat created by nuclear fission. Now, while that heat can definitely be used for other things, its main gig is generating electricity. If you really think about it, a nuclear reactor is essentially just a highly advanced, giant kettle. It's a wildly fascinating way to simply boil water and spin a turbine.
So how does that actually play out? Let's trace it step by step. It all starts with extracting raw ore and processing it into fresh fuel. You feed that fresh fuel into the reactor core, and boom, it generates an incredible amount of heat. That heat gets rapidly transferred over to a steam generator. The resulting high-pressure steam powerfully spins a turbine, which creates the electricity that zips out across your local power grid. But here's the absolute genius of the whole cycle. It doesn't just stop there. The spent fuel that comes out of the reactor is actually sent off for reprocessing. It's honestly a masterclass in sustainability. We separate out the useful fuel so it can be reused, and we isolate the remaining waste for safe disposal.
Moving right along to Section 2, thermal versus fast reactors.
When engineers are designing a reactor to pump out continuous power, they have to balance a ton of different criteria. The 2 biggest categories we look at are based entirely on neutron energy. On one side of the ring, you have thermal reactors. In these setups, most of the fissions are happening down in the electron volt or even sub-electron volt range. Basically, their neutron flux peaks at thermal energies. On the exact opposite side, we have fast reactors. Here, most of the fissions happen way up above the 10 kiloelectron volt mark, and the neutron flux actually peaks well above 100 kiloelectron volts.
So, what does that actually mean for the design? Well, it's all about how we control those speeds. Because thermal reactors operate at lower energy levels, they absolutely require a moderator to essentially pump the brakes and slow those neutrons down. Engineers usually rely on light water, heavy water, or graphite to get the job done. As a real-world example, most of the operating reactors in India are pressurized heavy water reactors. They brilliantly pair natural uranium fuel with a heavy water moderator. On the flip side, if you use light water, you have to use enriched uranium. But here is the crazy contrast. Fast reactors, because they operate at those massive high-energy levels, require absolutely no moderators at all. None.
Okay, let's get into Section 3, moderators, coolants, and cores.
With all that intense heat being generated, reactors absolutely have to have a robust coolant system to prevent meltdowns and to transfer that heat to the steam generators. For thermal reactors, you can cool them down using light water, heavy water, or even gas. Fast reactors, though, they require something on a whole other level. Fast reactors are mostly liquid metal cooled. Let that sink in for a second. Liquid sodium or liquid lead actively flowing through these incredibly complex systems just to keep the internal temperatures perfectly balanced. It's wild to think about.
But coolants are really just one piece of a giant puzzle. We also categorize reactors by their core arrangement. For example, are the fuel and moderator mixed together in a homogeneous system or kept strictly separated in a heterogeneous one? We can also track a reactor's entire life cycle just by its size and purpose. They start as early experimental and prototype phases, scale up to demonstration plants, and ultimately become full-scale commercial power producers. And we can't forget the stark strategic divide. Civilian reactors, built strictly to power our homes, versus military reactors, designed specifically to produce fissile material.
Finally, let's look at Section 4, the 4 reactor generations. When you look at all these complex classifications we just talked about, the coolants, the moderators, the core types, you realize these are just the foundational building blocks for engineers. As the tech naturally improves and these variables are relentlessly tweaked and refined, we organize reactors into distinct generations based entirely on their overall sophistication.
Let's walk through that historical timeline. Generation 1 reactors, those were your early prototypes, your research reactors, the ones that basically proved the science was even viable. Fast forward, and Generation 2 represents the vast majority of the current nuclear power plants operating around the globe today. Then we step up to Generation 3. These are the modern plants currently being implemented, and they are evolved entirely from acquired, hard-won experience. That experience directly translates into massive upgrades in safety, reliability, and cost-effectiveness.
But we are definitely not stopping there. Generation 4 reactors are advanced concepts that are under intensive study right now. They're designed not just for excellent safety and fuel economy, but with some truly groundbreaking new features. We're talking about systems that allow for online refueling and, most importantly, a massive minimization in the amount of toxic and radioactive waste produced. It really showcases the incredible forward momentum in this field, promising a much cleaner, much more efficient energy landscape.
So, when you consider the massive leap from the giant kettles of Generation 1 to the hyper-efficient, low-waste marvels of Generation 4, I want to leave you with this provocative thought. As we continue to relentlessly tweak the coolants, the moderators, and the core arrangements, which of these revolutionary reactor designs will ultimately power our future? Thank you so much for joining me on this explainer. Keep questioning, keep learning, and I'll catch you next time.